Guys, so this is our penultimate class, but Monday is review. So we're finishing what we're doing today, and Monday you're in charge of what we're doing. Also, I have scheduled office hours for both classes on reading day.
At the same time. Every fighter.
And I actually reserved this room, so you guys can have half the room, the other class can have the other half of the room. Tuesday, 1 to 3. Okay. So I want to finish up discussing the spectral theorem and relate it briefly to stuff we did last semester, not that anyone remembers. and then I think we're going to have a little bit of time left over, and I actually want to give you a preview of one of the most beautiful subjects in math, if I have time to do it.
What subject is that?
Complex variables, because it comes very naturally from what we're doing in here. So last time we stated the theorem. What did it say?
Any symmetric matrix A has
All real.
You started off so well.
Suppose a symmetric n by n matrix, such as a map from R into Rn, satisfies T of x.
You don't have to read it to me.
It has all real eigenvectors,
All real,
eigenvalues.
and
Has
all real eigenvalues.
Yeah. And there's an orthogonal matrix Q, where
Consisting of Q inverse AQ equals Q transpose AQ equals diagonal.
So it can be orthogonally diagonalized, is what I'm going to say to be short here.
okay,
Right? There's an orthogonal matrix that diagonalizes it. Question? Okay, so I want to give a proof. I want to talk about what it means and go on from there.
Should we put
So,
a star by this proof?
if you like, you can start. However, they will not. All the proofs that appear on the final will not just come from this last unit.
Well, a lot will.
I didn't. Well. All right. So there are purely algebraic proofs of the fact that the eigenvalues are real, but since we have all the beautiful calculus we've done in this course, I want to use it. So you actually did web work where you did this last semester, but you probably don't remember. Consider the function which we could call capital Q, but I'm going to call it F because that will fit what we did last semester. Consider the function which takes ax dot x, which is the same as x transpose ax, of course. And what I want to claim is, if we restrict F to the unit sphere, which is given as a level set of our function that takes length squared of x, what is true?
It has a local min and max.
It has a
Global.
global, right? Continuous function, compact set, you're guaranteed a maximum min. X must have a global maximum. And what must happen at that global maximum? How do you go hunting for the max point?
gradient 0.
Positive. So you can use Lagrange multipliers.
Lagrange multipliers. By Lagrange multipliers, at said maximum, let's say V, what occurs? How do we do Lagrange multipliers?
Gradient of f is some multiple of the gradient of g.
So gradient of f at this point on the unit sphere, v, is some multiple, which coincidentally we call lambda, of gradient of g at v. Did we write Lagrange with gradients or with d's? I don't remember.
Gradients.
We did gradients. Okay, cool.
Is there a reason, is the lambda supposed to make us think of eigenvalue a little bit?
What a coincidence.
Was that a sarcastic question, Mama?
No, seriously, is there a reason they're both lambda?
Uh-huh.
That's pretty cool.
So what is the gradient of g?
2x over 2x over magnitude.
So gradient of g is just twice the vector. Right? Gradient of g at x is twice x. Since I'm evaluating at v, for reasons that you probably suspect, the gradient at the point v is 2v. What's the gradient of this guy? Well, remember A is symmetric. So because A is symmetric, you go off and you do scratch work. We actually did this at one point last semester as well when we were doing these squares. The gradient of f is actually going to be twice ax. Because if you write down, just to see what's going on, if you write it out, a11 x1 squared plus twice a12 x1 x2 and so on, what are you going to get for the partial with respect to x1?
2a11.
And then when you take the partial with respect to x1, you're going to pick up all the middle cross terms. You're going to get twice a12 x, wait, twice a11 x1, right? Derivative of x1 squared. I need to stop listening to you guys. Derivative of x1 squared is twice x1. Derivative of this with respect to x1 is twice a12 x2, and you'll get similar terms for all the x1 xj's. So what am I getting here? I'm getting twice the first component of the vector a times x. First row, right? You multiply the first row of a times x, you get exactly this. So we're getting twice a v. So what do you see happens at the maximum point? Hmm? A v equals lambda v, in other words? So we recover an eigenvector. And the Lagrange multiplier has the neat meaning of being the eigenvalue.
So Lagrange multipliers are a cool way of finding eigenvalues in certain
So
situations.
you could actually apply, I mean, the trouble is, to actually solve the Lagrange multiplier problem, you have to find an eigenvector. You guys did a couple by hand examples of this in web work last fall. But I mean, you don't really, but you might have numerical ways of doing this. But it has a nice conceptual idea, because what you do is you look at this quadratic function, you maximize it, and then that gives you an eigenvector. How are you going to find the next eigenvector? This is what we're about to do in the proof. Well, you take the orthogonal complement of this one-dimensional space. You now maximize f on this one lower dimensional sphere. It has a maximum point, but because that also is compact, and you continue recursively, you find all the eigenvectors by successively finding maxima when you restrict the domain small and small. Okay, so we have an eigenvector with eigenvalue lambda. What does this prove?
Repeat at that point.
By taking the perk. Yeah, so, all right, so let's, what am I going to do? I have an eigenvalue with an eigenvector. So now we're going to do it recursively, or do induction. So now we have, and this is going to remind you of one of your homework problems that you just turned in. We have our first eigenvector. Claim. For any W that's orthogonal to V, so you take any vector that's orthogonal to V, and you multiply A times it, it's also going to end up orthogonal to V. Why is that? Well, how do you tell if somebody's orthogonal to V? Compute the dot product. What are we going to use? Ted's favorite formula. So this is equal to W dot
A transpose B.
But A transpose is?
A.
And what do we know about AV?
It's 2B.
No, it's lambda V.
Yeah.
And what do we know about W dot V?
They're orthogonal to 0.
So therefore AW is also orthogonal.
Should that be AW is not in the same deeper? Up there.
I said it, but I didn't write it. Yeah. So here's where the induction goes, right? That's going to be this picture. So what do? We say, choose a basis. And let's make it be an orthonormal basis for Rn with the first vector equal to V, and then just complete it to a basis any way you want, just so long as it's orthonormal. So let's let P be this change of basis matrix. What do you get if you compute the matrix in the new basis? So what is P inverse AP going to look like? Well, first column is going to be what does A do to the first basis vector in terms of the new basis?
Stretches it by lambda.
Stretches it by lambda and leaves all the other components 0. And then you have junk here. So this should be reminding you of homework that you did recently. But here's what's different from what you did in homework. What do you think is happening up here?
0.
Why?
Because everything else is in the curve for the next OB.
Good. So from what we proved here, if you apply A to any of these vectors that were orthogonal to V1, the answer is orthogonal to V1. So that says these are all zeros. It also is going to follow from a comment I'm about to make here. Note, chalk. Note, let's call this guy A prime for the minute. What is A prime transpose? This new matrix, what's its transpose?
We'll still be the lambda and the zeros and then.
It's gonna look the same as what we drew.
Well, no, but I want more information.
The junk will be transposed?
But let's just write down what this formula tells us.
E transpose A P inverse transpose.
right, what do we know about the matrix P?
Oh, the
P
transpose
is-
equals P inverse.
P is orthogonal, which means P transpose is P inverse,
So P inverse A, because A is symmetric,
asymmetric.
and then P.
So in other words, this new matrix is also symmetric,
Yeah.
which in particular tells you the zeros that Cameron said we'd already showed. But what we now know is this piece of A prime is symmetric. So now you repeat the process. Now you do induction. And that's the end of the proof. So now because A prime is of this form, let's just say B, where B is symmetric, we continue. And so now you pick a new basis for the perp. So the first vector for that is an eigenvector and keep going.
Why is it necessary that B be symmetric?
Because I can't continue unless I know I have a symmetric matrix and I apply the same process to it. If it were a random matrix, I'd be stuck. But because it's a symmetric, and B is a symmetric, n minus 1 by n minus 1 matrix, you can now continue and do the same thing. Officially, the math nerds in the room will say we're doing induction. So state this by induction on n. It holds for n equals 1, because a 1 by 1 matrix is already diagonal. Now suppose you knew it were true for every n minus 1 by n minus 1 symmetric matrix. Well, then we could prove it for an n by n case, because we are now at that point. If you knew you could diagonalize that thing, then we would have diagonalized A. So, done by induction. Cameron, do you have a comment?
Why do we know that B is not a zero matrix?
So what? I'm fine with that. It's already diagonal. Why are you worried about it being 0?
I don't know. It just looks like zero would be finding that value.
That's fine.
Those are real.
Those are real. You can choose an orthonormal basis for that Rn minus 1. Everybody's an eigenvector. Okay. So here's a neat interpretation of the theorem. So we're saying that we can write, if Q is our final change of basis, which makes basis of eigenvectors. So in fact, I'll call them Q's just to be specific. So the Q's are the columns of the matrix Q, and these are orthonormal. And they're eigenvectors. What does it say when we write this equation? Lambda is the matrix of eigenvalues, diagonal. Well, this is equivalent to saying A is Q lambda Q inverse, which is the same as Q transpose. So I want you to draw yourselves a picture of that, and then use your fingers. So what is this saying? A is Q lambda Q transpose. So I've got the columns of Q, which are these orthonormal vectors, and then I'm transposing that critter. So I've got Q1 transpose, Q2 transpose, down to Qn transpose. This might mildly be reminding you of something we did last semester, which I'm coming right back to in a minute. So not remembering it, no one's remembering?
Not yet.
Granted, we have diagonal matrix something, something transpose. It's the LDL transpose decomposition of a symmetric matrix again, which I'm coming back to in a few minutes. This is very similar. So how can you understand what this is doing? Well, think about what you're doing. This lambda 1 appears in what terms? When you multiply these matrices, what has a lambda 1 in it? If I think about doing this, it's only the first column.
Yeah.
And which rows from the second one appear?
First row.
Right? If you're going to do this multiplication and you want lambda 1 in it, you've got to only hit the first row, right? What's going to get you lambda 2 appearing?
Presumably second column, second row.
It's got to be Q2, second column, second row, here, and so on. So what you're saying is that you've written your matrix as a sum of these eigenvalues times eigenvector, eigenvector transpose. What are these n by n matrices doing? If you take a unit vector times its transpose.
Its magnitude.
No, that's in the other order. This is n by n. It's an n by n symmetric matrix, but what does it mean geometrically? And we did this last semester.
It's symmetric.
You take V a unit vector, and you do V transpose. That's an n by n matrix, right? N rows, n columns. Let's see what happens if you multiply it by x.
It becomes a dot product?
Times. This is the dot product. And then you're multiplying it by the unit vector v. What are you doing when you're doing that?
Projecting.
This is projection on the vector v. So this is the sum of each eigenvalue times the projection on the corresponding eigenvector.
Projections of what?
This is a linear map.
Right.
A wants to eat a vector x. This projects the vector x and adds it up weighted by the eigenvalues. So now if you have repeated eigenvalues, if you have lambda, a certain lambda appearing several times, you're then taking the lambda times the projections on the orthonormal basis for that eigenspace. So you're getting the sum of distinct eigenvalues here, project on the eigenspace, and multiply by the lambda. So you have a symmetric map. It has eigenvalues 2, 5, and -3. Multiplying by this matrix takes twice the projection of the vector on the 2 eigenspace, plus 5 times the projection on the 5 eigenspace, plus -3 times the projection on the -3 eigenspace. This formula here, A equals this, is called the spectral decomposition of A. And this is why I think it got named the spectral theorem, because of physical applications. These eigenvalues are like the spectrum that you see when you do spectrography. So if you do you take some combination of atoms, some piece of matter, and you bombard it with X-rays, and you measure at what frequencies things resonate particularly, and you get a graph frequency versus intensity. And when you see something that it doesn't care much about these frequencies, and it bloops up, and it goes along, and when it blips up, you're seeing the frequencies at which it resonates. Those are telling you the eigenvalues. Those are the spectrum. And this actually generalizes not just to the linear algebra we've been doing in n dimensions, but infinite dimensions. And there's actually a decomposition of symmetric operators on Hilbert space as an integral over all the different eigenspaces, and there might be a continuously varying bunch of eigenspaces where you weight the projection on each space by the eigenvalue.
So that, would those operators correspond to quote-unquote infinite matrices?
Yep.
Or no?
Yep. So that belongs in a graduate second semester real analysis course, so we're not going to do it. You're lucky.
Thank you.
But this is really cool, right? I mean, this is telling you that you can, if you're, so the physicist in the room might see an application of this where A was the Schrödinger operator, and you'd be actually looking at the spectrum of the hydrogen atom or something like that. But you're seeing this beautiful weighted projections. You're projecting, like we did last semester, onto subspaces, but you're putting coefficients that are the eigenvalues. Which makes sense. The part of the vector that you're doing that lives in the 2 eigenspace gets stretched by a factor of 2.
Yeah.
The part that lives in the 5 eigenspace when you operate by A gets stretched by a factor of 5, etc. So this makes perfectly good sense.
Why does it need to be symmetric for that to make perfectly good sense?
It's the orthogonality of the eigenspaces. And remember, we talked about this when we did Gram-Schmidt. If you have non-orthogonal vectors, you cannot project on here plus project on here and expect to recover your vector. So that's a great question, Ken. The symmetry is essential to get the orthogonality of the eigenspaces. Any questions on this? All right, so since I reminded you of what we did last semester, last semester we had the LDL transpose decomposition of a symmetric matrix. I don't truly expect you to remember the answer to this question, but I'll ask anyway. What was this based on doing?
Completing a square?
So we considered this quadratic form, just like we've been doing, and I think you said it.
Completed a
Yeah,
square.
we completed the square.
Yeah, it was hell.
And then there was this magic that putting stuff in reduced in echelon form gave you the same algebra. So let me just come back to the example we did Wednesday, and I'm not going to sit here and do all the work because you don't want to see me do it anyway. So we had our example from Wednesday. We had this matrix, 1, 2, 4, 1, -4 there, and then a -5 here, and we got that our eigenvalue matrix, our matrix, diagonal matrix of eigenvalues, was 3, 3, and -9. These are the eigenvalues. All right, and you'll just have to trust me. But I actually did double check with Mathematica, so I'm not lying to you. If I do LDL transpose, I get the following. And that, again, that comes from completing the square or from doing row reductions. You take your pick. Any observations you care to throw out?
The product of the diagonal of the cap, and I guess is the same as the product of the diagonal.
Okay.
The D's and the lambdas are all powers of 3, sort of.
Yeah, that's sort of a coincidence here, I think.
Okay.
Oh, well, not completely. But because I gave you eigenvalues that were just powers of 3 in the first place, this had no choice.
Okay.
But so I should have picked more generic numbers. But all right, so Reese is observing the determinants match. Well, that had to, because the product of these guys is the determinant of A. And if you compute the determinant of A from this, you get determinant of L, which is
1.
times the determinant of D, which is times the determinant of L transpose, which again is 1. So the product had to be the product. Reese, do you notice anything more besides what Daniel did with the powers thing?
I see the first column.
The number of signs matches.
Well, that's from L. That had to happen.
Just give me
The
negative.
number of signs matches.
There you go. The numbers do not match. Right? The numbers don't match, but there's one negative here and one negative here.
Isn't that mandatory though, like the same? I guess you could have 3 and 1, but if the
And 2 positives and 2 positives.
determinant's gonna be the same, you would move.
Well, I could have had a negative determinant with 3 negatives.
Right.
Yeah.
And imagine a 4 by 4, there'd be a lot more possibilities. So the beautiful theorem here, which is called Sylvester's law of inertia.
Did you just make that up?
No, I did not. Are you suggesting that I've lied to you all?
It's always a
At
possibility.
least one.
I'm sure that's just the number of positive numbers, zeros, negative numbers on the diagonals of D and lambda are the same.
So how does that deal with inertia?
Or so.
I think the language comes again from physics with the moment of inertia tensor, which is an example of a symmetric matrix. I mean, actually, inertia shows up also in algebraic number theory in a very strange way that you wouldn't even want to begin to understand at the moment. But I think this is coming from the physics.
So it's not referring to the numbers themselves.
No, so the numbers do not match up in general, but we did observe that the determinants have to match, so the products have to be conserved. Since Wyatt asked me a couple weeks ago for an application of homotopy, I thought I'd throw this in. And to understand why this is true is an application of homotopy.
On the space of matrices.
We're going to talk about, can we deform this matrix to this matrix without ever going across zero determinant? Well, look, here's this matrix L. Consider the matrix LS, well, let's call it T, since I called our homotopy T. Consider the matrix LT, where you take the same diagonals, but you put T in front of every coefficient here. So when T is 0, you have the identity. And when T is 1, you have the original L. So this is a straight line path in the space of matrices that goes from here to here. What happens when you consider L sub T times D times L sub T transpose?
It goes from D, L transpose to A. Smoothly.
Right, this gives a path When t is 0, you're at D. And when t is 1, you're at A.
I didn't see LT transpose.
Whoa.
So now, did this path of matrices ever cross non-singular matrices here?
No.
So I'm doing this. I'm doing the proof here for the case where A has no 0 eigenvalue, and you can jazz it up, but I'm not going to do that with you today.
No, it's always.
This stays non-singular because you're multiplying D, which is non-singular, by
Upper and
lower triangular and upper triangular matrices with 1s on the diagonal. So that means that whatever the eigenvalues of this thing are doing, they never cross 0. So it's a fact that follows from what we did in our stuff with winding numbers and homotopy. So that's chapter 8, section whatever it was, the last section, that the roots of a polynomial vary continuously with the coefficients. So as you vary the matrices continuously, the characteristic polynomials vary continuously. Therefore, the eigenvalues vary continuously.
What does that mean, very continuously?
If you wiggle the polynomial a little bit, the roots just wiggle a little bit. You can't have discontinuous behavior in the eigenvalue, in the roots of the polynomial.
Wow.
So if you have a polynomial, put a little disk around each of its roots. If you wiggle the coefficients, all the roots stay inside those disks. Counting multiplicities.
We get this, the lower triangle matrix, if they would only have Q lambda Q transpose. Down here we have.
This is using the LDL.
I'm doing the LDL transpose thing from last semester.
So L is completely different than Q.
Absolutely.
Because
Yeah,
it's not
absolutely.
but there's not eigenvectors.
Right. But so therefore, since the roots can't cross 0, because we stay non-singular, it means 0 is not an eigenvalue, the signs can't change. As you go through this path, the signs of the eigenvalues of this matrix have to stay the same as they were. Right? This 1 can morph wherever it wants, and eventually it's going to turn into 3. This -3 can morph wherever it wants, but it has to stay negative, and eventually it has to get down to -9. And this 27 has to stay positive and morph however it wants, but it has to turn into 3 eventually.
Switch around.
So it has to start positionally.
Yeah, who knows who goes where, but in the path, these two morph over to those two, and this one morphs to that one.
What about, you said that the number of zeros on the diagonal lambda agree? If one.
No. Oh yeah, so if you had had a singular matrix, there would have been a certain number of zeros here and a certain number of zeros here, and those would agree. I'm not proving that now, but I mean I could.
That doesn't just fall out of this, right? Because it could wiggle. Just our argument doesn't.
You can't wiggle 0 and stay 0.
Right.
All right, so I'll make a comment. The positive ones stay positive, and the negative ones stay negative. If you had a null space, if you had some zeros here, why would there be the same number of zeros here?
Because the positive ones stay positive. They don't match, so.
Well,
And the determinant has to be.
no, but my proof was looking at the characteristic polynomial, and if it has 0 as a root, I can't say that I can't cross 0, because things could cross through 0 from positive to negative. So you have, here's the idea. If 0 is an eigenvalue. Consider A plus epsilon times the identity. Change the matrix to shift the eigenvalues off of 0, but make sure you didn't make any of the negative ones come up to 0. So make sure that the epsilon is smaller than the smallest absolute value of the diagonal things on D. So whatever the smallest and absolute value -1 is, make sure the epsilon can't drag it up to 0. Now you've pushed all the zeros up to positives, so all those will stay positive. The negatives stay negative, so the negative number has to stay the same. Now come back down, let epsilon go to 0, and you get the conclusion. Sort of a sneaky idea. Yes, sir?
That one kind of comes from the proof we did in the homework for the upper diagonalization, so we can wiggle that around to get.
I'm not using that at all here. I'm saying specifically, if you had a 0 eigenvalue here, then this would have to have at least 1 0, because the matrix would have to be singular. And now what I'm saying is, perturb the matrix A by adding a small multiple of the identity to knock all the zeros up, so there's no more 0 eigenvalues.
Or down, you can knock them down.
You could move everybody down, but you have to make sure
Yeah.
you're not introducing any new negatives. Okay, so this is actually a surprising result. When I first saw this, when I was a little older than you guys, I was pretty impressed.
What about Sylvester?
Sylvester was doing a lot of serious multilinear algebra. He was happy with it. Okay, so just to tie a little bow on the course here.
Oh, that wasn't the bonus thing?
This wasn't the bonus.
Oh, okay.
Mm-hmm.
Wait, Alice, yeah.
This is the encore.
So, obviously in 8 minutes I don't have time to do justice to what I'm going to say here, but I want to show you that the multivariable part of the course leads to some really cool stuff, and I'm obviously not proving anything, but I'm going to say a few things here. So, one of the natural places that the Stokes theorem stuff leads is to studying of smooth, complex valued functions on C. So you could do everything we've done in calculus, studying functions from R2 to R2. But instead of thinking of it as a vector valued function on R2, I'm going to think of R2 as a copy of the complex numbers. And since I've introduced you to complex numbers talking about eigenvalues, I figured why not? So simple example would be write Z as x plus iy and think of a function of Z. Well, here's an obvious function. What's that otherwise called? The identity. Here's another function, not so obvious. Z bar. So for those of you who don't know what that is, you're going to take the imaginary part and negate it. What is that doing geometrically? It's taking a complex number and reflecting it across the real axis, across the x-axis. Turns out, from the viewpoint of what we did in calculus all year, there's not much difference between these two. I mean, you could quibble that the derivative matrix for this one was reversed orientation, because it's a reflection. But, you know, they're both pretty tame. Well, we say F is holomorphic, nice word, if you take the complex derivative in the sense of the limit using complex numbers, right? Our old limit definition that you learned in Calc 1, but you just take complex numbers here and you say this limit exists. What magically happens, and I'm not going to take the time to show you this, I could, it's easy, is this happens if and only if the derivative matrix, thinking of this as a map from R2 to R2, has this form.
Skew symmetric?
Not skew symmetric. I guess I'll write it this way because then it looks like your homework problem. You remember the homework you just turned in? Where you saw if you had complex eigenvalues, you could put the matrix in this form with alpha and beta? So it turns out that this limit definition says the derivative matrix as a linear map from R2.2 has this very special form, which corresponds to multiplication by a complex number. So this linear map is multiplying by the complex number, which would be the derivative. All right, so here's what I want to show you, because this is cool. Write out df. Remember this? Let's review for the final. What's df? It's partial with respect to x, dx, plus partial with respect to y, dy. Now, in this case, f is a vector function. It's got, right? It's got complex values. But now look, I don't like x and y anymore. I like z's. So I'm going to say to myself, if I wrote down z, I could take d of it, and I would have dx plus I dy. And I could write down z bar, and I could take d of it as a complex function, and I would have dx minus I dy. And to save a few minutes, I'm going to skip the algebra here. You could rewrite this as something or other times dz plus something or other times dz bar. Right? Just substitute what dx is in terms of these. And substitute, it's a change of basis. Substitute what dy is in terms of these. Regroup, and you'll have so many dz's plus so many dz bars. It's going to turn out that f is holomorphic if and only if this stuff here is 0. In other words, there's no dz bars appearing when you take the derivative. It's just dz's. So the fact that you have a limit in the complex sense means that when you take the derivative, there's no dz bars. Well, I'm now going to tell you the punchline of that. Suppose you wanted to take a curve that was the boundary of a region. What theorem is this sounding like? Or Green's theorem. Here's a one form. Integrate the one form over the curve. By Green's theorem, it's the integral over the inside of d. That's a one. It's a combination of dx and dy. Take d of this. What's the rule? The rule is you take df wedge dz. Well, which part of df is going to show up here? Only the dz part, because the first part is dz wedge dz here.
Oh wow.
So this is going to turn into star dz bar wedge dz. Well, we said holomorphic functions meant that the star part was 0. Is this looking familiar, Michael?
Yeah.
So this is 0 whenever, and in fact, if and only if, f is holomorphic. So the integral, when you start with a holomorphic function, a nice complex differentiable function, integrated dz around any closed path that bounds a region, it has to be 0. This leads to all sorts of fabulous stuff. Okay. And of course, we're done.
If